So let's do an imine synthesis. So first thing I'll show is an aldehyde plus, I'm just going to say, an amine, methylamine. And we're going to have some H plus that's going to be a catalyst. Right, so this is the first time we're looking at this. I'm going to tell you what the product ends up being so we kind of know what we need to get to. So what is an imine? So this is an imine. Right? Essentially what's happened here, the C double bond O has been replaced with a C double bond nitrogen. Right? And you can also probably guess what else should be the byproduct here. There should be an H plus, right? We should have catalyst regenerated plus H plus. What else do we need? I think we'll need a water molecule, won't we? We also generate water. Right? It's a condensation reaction. Right? Because remember we start with H plus, so that's a catalyst, so we had to make that again. We lose an O, and this N has two H's on it, right? Here it has no H's, so that becomes water. So it's a condensation reaction. We have to lose water at the end of the day. So this is what we're trying to make. Right? And so this is basically going to be just like we did before. We're going to use proton transfers to make this happen. Right? So the first step will be, what do you think the first step is going to be? All these reactions protonate what? Carbonyl, right? Because that's going to make this a better electrophile, right? And the end of the day, this has to be an electrophile. So we want to make it as good electrophile as possible. So the first thing we're going to do is grab that H plus. All right, so now we got our amine, and we have our aldehyde, which is now even more reactive, right? Because we've protonated it, so we've made that carbon, right? The whole point of acid, again, is to always make the carbonyls more electrophilic, and that's what we've done. So now we can have the amine attack. And somebody might say, well, why didn't the amine just attack this? It could. But then that goes back, right? This is a non-productive pathway, right? At the end of the day, we're trying to make this. So what bond, actually we talk about this too, I said before I get too far. What bonds do we need to form in the products that are not in the starting materials? What new bonds do we make? So a pi bond and a sigma bond to the CO is broken. What else are we going to make? Right, so we need to break a pi and a sigma bond to O. We need to make a CN double bond, right? Sigma and pi bond. Right, we obviously need to make water molecule at some point too. Right, so water is probably going to be our leaving group. And again, these are equilibrium reactions. So we can start thinking about, well, if I wanted to make this reaction go, what would you want to do? What are some things you could do with an equilibrium reaction? We already have a catalyst, so there's that option. What else can we do? Take out the products. What's the easiest product to take out? Water, right? Water, always. Okay, so we have a tetrahedral intermediate. We want to balance our charge, right? So the charge should be on the nitrogen, right? Okay, and then we know though, right, again, tetrahedral intermediate. We want to do a proton transfer because we know at the end of the day, what do we need to get rid of? We need to break these bonds. So let's work on breaking those bonds. Right? It's not clear unless you see the product, kind of where you're going. All right? So we do a proton transfer, which we could even show if we really want to get crazy. Right? So now water is the best leaving group. But the problem here is a little different than we've done before, right? What lone pairs are going to have to come down? The nitrogen lone pairs, right? So the nitrogen lone pairs come down because that forms that pi bond. And then our water leaves. Yee. There's still an H here, plus. We just made water as well. And we know we're not done with our mechanism if we have a catalyst, we're not done until we've regenerated that catalyst. Good. So those electrons just go back. All right. You get to the product imine.
Can you regenerate it in the step before that? Like when you kick out the water? Can you like kick out the H2?
Yeah, you could, so you're talking about like maybe draw like these electrons just go here and it
Yeah.
all happens at once? Yeah, you could, sure. We talked about imines, let's talk about enamines now. So an enamine, let's say we start with a ketone this time, not an aldehyde. And instead of using a primary amine, we're going to start with a secondary amine. Same deal as before. H plus is a catalyst. But now our product is going to be a little different. It's going to be this. An enamine. Plus, H plus, and then plus again, we're generating water. Right? This is called an enamine. Right? When secondary, right, the key here is a secondary amine instead of a primary amine. Last problem we had a primary amine, so amine bonded to 2 carbons now. We're gonna get enamines in acidic conditions. Right? Again, equilibrium, drive off the water, blah blah blah. But the same ideas hold true, but there's gonna be a little something different here. I'll show you guys what happens. So, first step, right? We protonate. We grab that H plus. Good. So that, of course, makes the ketone a better electrophile. That's the whole point. Now our nitrogen will attack. Lone pairs attack there. Kick up. Get our own tetrahedral intermediate. Plus charge on the nitrogen. Right? Tetrahedral intermediate. Right? If we have a good leaving group, it'll leave. Or if we want to switch leaving groups, we need to do that. So we'll do a proton transfer again here. Now we've created water as a leaving group, right? Because we knew we needed to lose water. At the end of the day, we're trying to break the oxygen sigma N pi bond. All right, now at this point, we want to bring down the nitrogen lone pairs, right? Because we're trying to make that pi bond again. So very similar to the imine, right? Very similar to the imine synthesis so far. But now there's a plus charge on the nitrogen. We just lost water, right? Yep. So we know we're not done with this synthesis until when? And we haven't done that yet. Right? We don't have H plus yet. So what we're going to need to do, though, is if you look here, this carbon has how many hydrogens bonded to it? 2. How many does this carbon have?
3.
So that's where it must be coming from. This carbon right here has 2 hydrogens bonded to it, right? This one has 1, 2, 3. So this guy had to lose a hydrogen. So this is what happens. So imagine, right, here's H. Right? It leaves, right, forms that pi bond, and at the same time, right, if you make a bond, you gotta break a bond. So the electrons come back to the nitrogen. And now you have your enamine. Right, which is neat. Now this is why there's a reason why this is important. Does everybody see how that we lost that H plus and now there's a double bond there? Right? We've kept track of our atoms, balanced our charges, all that good stuff. The neat part is this carbon right here. Do you think this carbon is going to be is it going to be a nucleophile or an electrophile? Because that's a pi bond now, right? What do you guys know about pi bonds? Are they nucleophiles or electrophiles? We just did some more Oompa in chemistry. Right? Ketones are normally electrophiles, right? But now we just turn into an enamine, which is nucleophilic at this carbon. Nice.